All right, we're back. We're on Calc AB Notes 5, page 5. We're solving some very traditional looking mean value theorem problems, and nothing wrong with that. So let's take a look at this one. So we want to, what are the directions? If you can apply the mean value theorem, apply it, or state it in the context of the problem, then apply it to find the value of C. So, all right, not really obvious if you can apply it on this one. So x squared minus 2x plus 4. Does this thing, so this is, it's quadratic. Let's see. Let's just use the calculator. We got to figure out the domain of this thing and make sure that like the values that we're dealing with are in the domain. So how can we do that? We can type domain natural log 4 plus 2x minus x squared. Could have like completed the square or something like that. I just don't feel like it. Negative 1 point something to 3 point something. Phenomenal. All right, so the only issues that we would have really are at those endpoints and then beyond that, so we're good to go. So I'm going to say that, so I'm just going to assert that we can use it. And I do that a lot. If I don't feel like proving something, I just confidently say that it must be true, and kind of go with it. Let me use this color to start with. So f of x is continuous on the closed interval, differentiable on the open interval, therefore by MVT. I feel like I've got a better sense of the geometry of the page here, so I know what to do a little better, maybe, potentially. F prime of C equals f of 3 minus f of negative 1 over 3 minus negative 1. Now, some people like to find this value so they can like write it down on here. I'm going to not do that. Well, for this function, for sure. And you'll see as we do, our method will evolve as the problems become a little more detailed. But this is definitely true, right? Functions continuous on the closed interval, differentiable on the open interval. Therefore, the mean value theorem applies. It guarantees that the slope of the tangent line, f prime of c, is equal to the slope of the secant line, f of 3 minus f of negative 1 over 3 minus negative 1, for some c between negative 1 and 3. And you're good. So now I'm going to just use a calculator to solve this. So I'm going to say f prime of c, whoa, sliding on me, equals f of 3 minus f of negative 1 over 3 minus negative 1 gives me c. I think this is probably going to end up an approximation. I'm going to go to the calculator. I'm going to review a little on the calculator here because I've done a few things. So the first thing that I have done is I've actually stored a weird function that I've called MVT, and it's a function of a and b. And what it is it's solving the mean value theorem equation, right? Slope of the tangent line, so the derivative with respect to x of f of x is equal to f of b minus f of a over b minus a. So I just need to reset what f of x is, and then I can use this function. So I'm going to do that. So f of x is this crazy natural log function. Derivative of natural log, 1 over u times the derivative of u. So in this case, it would be 1 over 4 plus 2x minus x squared times the derivative of that, which is 2 minus 2x. So that would be the derivative, but we're never even going to see it because we're just going to use our MVT program and go from negative 1 to 3, and I'll press enter. Oh, and you get like exactly 1. Well, that's weird. It's probably telling me more answers might exist, or the domain. Yeah, domain's always a mess with natural logs. So we get 1. And let's look at it graphically and see if that makes sense. So when you're not sure, like you go through the things you know how to do. Here's f of x. That's weird. So I didn't actually need to look at that. I need to look at the derivative of natural log. So let's do derivative. You can just use the template, and you should. Derivative, okay. And then f of 3 minus f of negative 1 over 3 minus negative 1. Get that. Oh, look at that. Oh, is that 0? It is. F of negative 1 is 0, and f of 3 is 0. So we could have done this by hand. I wimped out because I didn't want to deal with natural log. But yeah, we definitely got our answer. So we're going to say that c is equal to 1, which is what it asked for. So I'll say is the value guaranteed by MVT. So sometimes there's more than one value, sometimes there's only one value, but if something is guaranteed, it will happen. All right, let's look at this one. So we got to know what cosecant looks like. I'm not going to wimp out on this one. So to graph cosecant, it's a good idea to start with just sine. So sine, and let's dot that in. I'll dot it in blue. So sine looks like this. Okay, which means cosecant is the reciprocal of that. So all the zeros of this graph become the vertical asymptotes of cosecant. And you can see we're going to have a problem, and that's fantastic. Because honestly, when you're doing mean value theorem problems, you kind of want it to not apply, because if it doesn't apply, all you have to do is state the reason that it doesn't apply. This one has all kinds of issues. All right, so I'm going to say f of x is not continuous. What am I spelling there? Not continuous on the closed interval. It's got a discontinuity. Pi over 2 to pi over 2. Because f prime of, not f of 0 dne. Because f of 0 does not exist. Okay, so what does that mean? That means the mean value theorem doesn't apply. Therefore, MVT does not apply. You don't say does not apply often enough for it to have an abbreviation, really. So great, we were able to do that one really quickly. So had to remember how to graph cosecant. Start with the graph of sine, and then just kind of like invert everything. You're graphing the reciprocal function. So it's always worth reviewing that every once in a while. Like it doesn't come up that much, but when it does come up, you don't want to freak out. So what would cause a problem here? 0 in the denominator, so x equals -1. X equals -1 is not between -1/2 and 1/2, so we're good to go. So I'm going to say f of x is continuous on the closed interval, differentiable on the open interval. Therefore, by MVT, I don't know why I'm cramming this here. I'm going to keep cramming it. F prime of c equals f of 1/2 minus f of -1/2 over 1/2 minus -1/2 is just 1 for some c, which is an element of -1/2 to 1/2. So guaranteed this will happen at least once. Could happen more than once, but guaranteed once. So before I take the derivative here, what I'm going to do is I'm going to rewrite f of x. So I'm going to do +1 -1 trick. F of x is x plus 1 minus 1 over x plus 1, which is 1 minus 1 over x plus 1. Okay, and then I'll take the derivative of that, kind of in my head. So f prime of x is going to be +1 over x plus 1 squared. Okay, why is it positive? Because it's the derivative of 1 is 0. I'm thinking of it as negative quantity x plus 1 to the negative first. Bring the exponent down, negative times -1, +1, then subtract 1. You get -2, but bring it down to the denominator. So that's where that's coming from. And then f of 1/2 is going to be, f of 1/2 is not super easy to find. I'm going to find those on the side. So f of 1/2 is, oh, you know, I could use the simplified version. I don't really think that's better. You get 1/2 over 3/2, so you get 1/3. And then f of -1/2, you get -1/2 over 1/2, which is -1. Okay, So what color should we use? Let's switch to blue. 1 over x plus 1 squared equals f of 1/2 is 1/3. So 1/3 minus -1. So 1/3 plus 1 is 4/3. And then over 1. So just 4/3. Okay. And then that means x plus 1 squared equals 3/4. Took reciprocals of both sides, which is how I love to deal with that. And then we get x equals -1 plus or minus. I'm going to make it radical 3 over 2. Can we? Okay, so -1 minus something is definitely out of the interval because -1 is already out of the interval, and subtract something you're even farther out. So it must be -1 plus root 3 over 2. I'm going to say, therefore, c equals -1 plus root 3 over 2. Should we check it? I think we should. Let's see. It's always, man, like, this is the tensest moment in any given problem that we do. So I got to redefine f of x, for me at least, where I'm like, oh, let's see if all this work was worth it. Especially because I do like one long take, so like screwing up now, poof, just don't want to. We're gonna use our MVT function that we kind of like built in here, -1/2, comma 1/2, and this. Okay, and I get either -1 minus radical 3 over 2 or -1 plus. It doesn't know. If we go back here and we say that -1/2 is less than x is less than 1/2, it'll spit out just the one that we want. But I don't think that's worth it because we're humans and we can look at it and we can work it out. But you could do that, and it wouldn't have been hard. Like, we could have done it back when we defined the whole thing. So here we could throw in, I think you can throw this in. I'm not actually sure what the order of operations are here. B is less than x is less than a. Let me see. Let's do this. Undefined. Let's not do that. So get out of there. All right, it's back to working. So I don't know what it was doing there. So yeah, there. That's better, right? Do it, put it on at the end if you want. I just think you're best off like looking at it. I'm gonna do the last 2 problems on the page just to, like, you know, finish the page, because why not? And then we'll take a break, come back in another video, see if we can do it. These problems made it explicit, but often the fact that you must use MVT is not explicit. Blah, blah, blah. All right, so those are very like textbook standard problems. You will see those from time to time. It's not, honestly, it's a little unusual to do mean value theorem problems like that, but that's very much how it works. So let's see if we can do this. Find each derivative and simplify as much as possible. You know what you could do here if you really want to make this an easier problem? I'm going to do this one 2 ways. So one way is I'm going to do +8 minus 8. Why am I doing that? Let's see. 2x plus 3. God, 3s, man, so hard. +8 minus 8. Minus 8 over x. Why won't you write anymore? X minus 4. Okay, and then this I can rearrange. So already you're probably thinking, is this worth it? I'm also thinking that, but I'm going to do it anyway. As 2x minus 8, or 2 times x minus 4, and then plus 11 over x minus 4. And now maybe it's becoming a little clearer. So this is 2 plus 11 over x minus 4. Okay, what's the derivative? So then f prime of x is going to be just -11 over x minus 4 squared. So I thought of it as the derivative of 2 is 0. Make it 11, the quantity x minus 4, to the negative first. Bring down the exponent, -11. Subtract 1 from the exponent, so to the negative second, but then write it in the denominator. So that's one option. That's the +1 minus 1 trick, but like advanced +1 minus 1. I knew that I needed to get an x minus 4, so that's why I went with 8, because I knew I would factor a 2 out. So you don't have to do that, though. There's no reason to do that, because also the +1 minus 1 trick is literally just avoiding doing division. If you did long division or synthetic division, whatever type of division you want to do on this problem, you would get the same result as the result I get from using the +1 minus 1 trick. I just think it's faster. It's really fast if you don't also pause to explain the trick every time you do it, and you just like do it. I'm going to use the quotient rule on this to demonstrate that you don't need to do any of that. So f prime is actually, or is also, bottom derivative of the top minus top, which is 2x plus 3, derivative of the bottom, all over the bottom squared, which is, so this is the more traditional way. I get 2x and then minus 2x. I get minus 8 minus 3, negative 11, x minus 4 squared. And that was like way faster. So I didn't really save any time by using that trick, but I use it all the time. I love that trick. It's like my favorite. That's my favorite, like, non-technique technique of integration. Like, you look at it and you're like, oh, I got this. Should I do 2 colors on this? It's really annoying to bounce back and forth. So the caveat with this type of problem is that there's always a secret hidden critical point, right? So the critical points of this are definitely going to be negative 1/2 and 3/4. But there's going to be another one, at least one more. There could be 2 potentially. Well, no, not in this case. But you can almost see the critical points, but you have to do the problem. You have to factor to like get to what's happening. So you know what I'll do? I'm going to do it, and I'll highlight to show things. So first, derivative of the second. So it's going to be 2 times that thing to the first times negative 4. So I'm going to make it negative 8, 3 minus 4x to the first plus second, 3 minus 4x. What is happening? Squared times derivative of the first. So it's going to be 3, that thing to the second, times 2. So I'm going to write 6. I'm like too close to the edge. It doesn't like that. 2x plus 1 squared. Okay. And now, so where did everything come from? First, derivative of the second, plus second derivative of the first, and then first derivative of the second, plus second derivative of the first. So that's where everything came from. Now let's factor. So f prime is, we can take a 2x plus 1 squared out. Well, we can take a 2 out. I often don't do that because I find it easier to like, it's a little less to keep track of in your head if you don't take out that 2. And in the end result, you'll get the same thing, but we're taking this out to get 3 minus 4x to the first. All right, what are we left with? A negative 4 and a 2x plus 1, so negative 8x minus 4. And then what are we left with on the second thing? We're left with 3, and then 3 minus 4x, so plus 9 minus 12x. So this is 2x plus 1 squared, 3 minus 4x. Whew, negative 20x. That's weird. Negative 20x plus 5. Oh, there's more factor. I hate that. My least favorite thing is when there's like more factoring at the end. I'm like, could you have anticipated that? I don't really think so. I'm going to take out negative 5, negative 10, 2x plus 1 squared, 3 minus 4x. I took out negative 5, so I'm left with 4x minus 1. I believe that is the most simplified version of f prime. Should we check it? I think we should. Let's do that. Let's go to the calculator. I like this little should we check it thing that we like to say. Who are we? I don't know. So I'm just going to go straight derivative. There's no reason to like store the function. 2x plus 1. If I was going to do stuff with a function, I would definitely store it first. But, since all we're going to do is take the derivative and see what we get. Positive 10. Uh-oh. Oh, I see what the difference is. They have positive 10, 2x plus 1 squared. Positive 4x minus 3. We have 3 minus 4x. Same deal, right? They take a negative out of that. We have a negative 10. Good deal. And then a 4x minus 1. So we both got it. We got it. The calculator got it. Nice. Let's go back here and just give you a shot. Take your screenshots. There you go. And then, can we get it all in one? Yes, I think so. Take your screenshot of that. I will be back in the next video, and we will keep going. So I hope you're finding these helpful.